Today's lesson is on segments and congruence. So we have a new vocab word that we need to talk about. It's congruent. Congruent just means same shape and same size. Same shape, same size. So when we look at this rectangle up above, do you see any segments that are congruent to each other? For example, segment AB. Is that the same shape or the same size as any other segments? And what you should have said was that segment AB is congruent to segment DC because they're the same length and they're both segments. So that's what congruent means. There's a special symbol for congruent. You know how this means equal, like equal numbers? This means approximately equal to, like when we're solving an equation. So the symbol for congruent is kind of a combo of both of those. It looks like this, and that means congruent. So on that picture, we could say that segment AB, segment bar on top, is congruent to segment DC with a segment bar on top. And the other pair that's congruent is segment AD is congruent to segment BC. One more thing, there's a way that we can mark that on our picture to show that AB and DC are exactly the same length, that they're congruent. We're going to put a little mark that looks like this, and that shows me that those are congruent. I call those tick marks. So that would tell me on that picture that AB is congruent to DC. And then I can't just use a tick mark over here. That would say that all four of them are congruent. So instead, if you have another set, we could double tick these two. And that shows that those two match up, that those two have congruence to each other. I get super picky about one thing. Can you see the difference between this and this? We know that if there's a bar on top, that means we're talking about a line segment, right? But what if there's no bar on top? If you forget the bar on top, that means something different. It means that we're talking about the length or the distance from point A to point B. So let's look at an example of that. So down here, you'll see we have two segments, and you see the tick, tick. So that tells me that those are congruent segments. So let's write our congruence statement. Segment AB is congruent to segment CD from that picture. Let's talk about their lengths. If we say AB and we don't put a bar on top, that means the length, like if we took a ruler and measured that. If we measured from C to D, wouldn't you expect those numbers to be the same? And when we talk about, like, maybe this one is 3 inches and this one is 3 inches, when we talk about numbers, we use an equal sign. So I would want you to use an equal sign when you're talking about lengths. And I would want you to use a congruent symbol when you're talking about the actual segments themselves. So just to recap, when we're talking about length, we use equals. When we're talking about actual segments or shapes, we use the congruent symbol. Our big exciting thing for today's lesson is that we're learning our first postulate. And we're going to gain a lot of those this year, but this postulate is called the segment addition postulate. By the way, a postulate is just a rule that's accepted without proof. Postulates are kind of obvious. Later we'll talk about theorems, which are rules that we can prove. But this postulate, I think you'll agree with it once we figure out what it says. It says, if B is between A and C, then the length of AB plus the length of BC equals the length of AC. If the length of AB plus the length of BC equals the length of AC, then B is between A and C. That sounds super confusing, but the picture will help. So let's look at the picture and what they're trying to tell us. They're saying that the length of AB, the distance from A to B, plus the distance from B to C, they're saying if we add up those two lengths, we should get the length of segment AC. And I think that's pretty obvious, which is why we're calling that a postulate. So if we said that AB plus BC equals AC. We already know that AB measures 4 units from this picture and BC measures 7 units for this picture. Kind of obvious, do you think? That 11 would be the length of AC. Again, that seems kind of obvious, but when we're building our system of logic, we have to put a name to everything. So that's the one we're going to call segment addition postulate. Say it out loud. Segment addition postulate. All right, one last problem. There's a couple things to learn from this. One is that labeling your diagram, drawing in the numbers, can be really helpful. Right here, there's no bar above that RT, so that means that the length of segment RT equals 12 units. So from R all the way to T is 12 units. And from S to T is 9 units. Can you figure out how far it is from R to S? And hopefully you can see that that should be 3 units. And what we're going to do is we're going to explain why that is. So we're going to use our vocabulary, we're going to back up our argument. So that's what this little thing is over here. This first step, do you think you could convince me that the length of RT, this entire thing, is equal to the length of RS plus the length of ST? That should sound familiar. There's actually a supporting reason that tells us that the entire segment length is equal to the 2 smaller lengths added together, and that is the segment addition postulate. So we would use that to justify that reasoning. Next, it says that we can make a substitution. So do we know the length of RT? Do we know the length of ST? Those were given to us, right? So we're going to replace, substitute 12 for RT, the length of RT. RS we don't know yet. That's what we're trying to figure out. And we are going to substitute or replace the length of ST with 9. Those were what were given to us, right? Now, here's a tricky step. Can you see how we could make it from that equation to this equation? Should be a little bit of algebra, right? Do you see how this RS is all by itself now? What happened? What happened is we subtracted 9 from both sides of the equation. And there's a reason to back that up. It's called the subtraction property of equality. And that says that an equation stays balanced if you subtract the same thing from both sides. So that's just a fancy way of sort of showing our thinking in math and using the segment addition postulate at the same time.